were able to have our samples. This is the sample PP1. This is we took the sample PP2, and this is where we took our sample PP5 on the surface of a laying block. Now, most important are the samples PP1, PP1B, and they are still, we broke some pieces for the SEM examination. You look at the perfect surface of the sample. If we look under the optical microscope, this is what we see. When I first looked under the optical microscope, I was struck. Nobody has looked with optical microscopy on the surface of these unique artifacts. It's strange. They are claiming this has been done by the aliens, they are claiming and so and so, there are no tool marks, nothing, but they did not take the time for looking under just the optical microscope. What you have here, you see in white, these are the plagioclase crystals, and in between we have holes that are in different colors. It is a surface that is very plain, uniform, leveled, but full of holes. This is PP5. We have the white plagioclase, and in between holes that are 0.2 to 0.5 deep with clear walls, and underneath we see the crystals of the material. If we look on the cross-section, you see on the surface, and you see the holes up to 0.5 millimeter depth. But in other cross-section, we have the holes inside. So this is a material that is typical for these artifacts. Looking at the thin section, it is beautiful under the polarizing light, better than sandstone. You see in white the minute plagioclase feldspar crystals, feldspar and plagioclase crystals. Then here the big amphibole crystal, these are minerals, pyroxene. And we have a lot of black spots. These are amorphous substance. Under the scanning electron microscopy of the PP1 sample, we just see, this is a 5 micron scale, the small crystals. If we make the ADS analysis, we find that it is feldspar plagioclase. Now, we continue our investigation. So, to look at the surface is boring. It is more interesting to look at the holes, what is underneath. And we had our point 1, 2, 3, 4, 5, and then 6 and 7. I will focus on point number 4. Focus on point number 4 at a higher magnification. So we have in black, this is the hole surrounded with feldspar crystals, and in fact it is made of several different minerals. And if we compare this microscopic view with the SEM view, this is exactly what we have. So you see that on the left we have the plagioclase, this is the white body, H, it is a hornblende, this is a crystal. PA is a pyroxene augite crystals. SEI is ferrosilicates. And in between the midst of that, we have something that does not correspond to any classified mineral from the optical microscope. And we will focus on it, and we'll get a great surprise. We get the surprise of having a totally amorphous element that looks like rubber, gummy, anything. And we performed ADS. We got a high amount of carbon. We got nitrogen. We cannot measure quantitatively nitrogen, but qualitatively we can see that we have nitrogen. So it could be ammonium organic matter. So we are finding an organic matter in a volcanic rock, which is against nature. So it is man-made. One could argue that since this is a dot, a point that was on the surface, that what we had been measuring was the result of surface pollution. And then, in order to cope with this argument, we went inside. So you see the sample tray that supports the sample, and we went inside and had several spots. Spot number one. Well, you see the black system, all around is feldspars, and we have on the top of the black surface a crystal element. We have A and C analyzed. It is plagioclase. Then we analyze number B, that is underneath. It is organic. So we have feldspar, plagioclase on the top of an organic matter. This is inside the stone. Another point, we have a very smooth surface that could be the surface of a binder. And we have the dark spot, so we focus on the dark spot. Organic, carbon, nitrogen. Spot number 3, we have the same. Carbon, nitrogen, and other elements. Everybody will agree with the fact that this organic matter suggests the presence of an artificial stone. So, first conclusion, which chemistry? It is not polysilate-based geopolymer, like for the red sandstone megaliths. It is not the alkaline medium. If it is not alkaline medium, then it is acidic medium. And yes, this is acidic medium if we rely on the ancient legends that archaeologists don't take into account. Una substancia de origen vegetal capaz de ablandar las piedras. Plant extract capable of softening stones. This is what the local South Americans are telling and reading. Crazy. So they can soften. 42 years ago, I met a Peruvian anthropologist, and we decided to make our first presentation paper at an archaeometrical conference in New York. So we had a second in 1982 that reads, the first one, fabrication of stone objects by geopolymeric synthesis in the pre-Incan Huanca civilization in Peru. It is now agreed that the Tiwanaku civilization is modeled on the pre-Incan Huanca civilization, revealed by an extraordinary skill in fabricating objects in stone. A recent ethnological discovery shows that some witch doctors in the Huanca tradition use no tools to make their little stone object, but still use a chemical dissolution of the stone material by plant extracts, carboxylic acid. 1 year later, I made a scientific study with the Laboratory of Pharmacognosy in Grenoble, the disaggregation of stone materials with organic acids from plant extracts, an ancient and universal technique. So we studied what type of acid do we get from plants? And the conclusion was the pre-Columbian farmers were quite capable of producing large quantities of acid from such common plants in their region as fruits, potatoes, maize, rhubarb, rumex, agave americana, these are the cactus, ficus indica, oxalis pubescens, and we know that there are more now. So we will have carboxylic acid, acetic acid, oxalic acid, citric acid. This works perfectly for limestone. Limestone is disaggregated by this organic acid, no problem, very easy to prove. Any stone that contains limestone will be disaggregated, but not volcanic andesite. It doesn't work. So if it is the chemistry is used, it is only to fabricate a binder that will agglomerate non-consolidated stone material. Then it is okay. So clear cut between limestone and volcanic. Do we have archaeological hints suggesting that this idea is not crazy? Archaeological evidence on extensive culture of maize for possible manufacture of vinegar, acetic acid. Another expert, specialist of the region, this is an American, the experts are American archaeologists. Each one is specialized in one site. Paul Goldstein, Department of Anthropology, University of California. From stew eaters to maize drinkers, the chicha economy and Tiwanaku. The chicha is the very well-known local beverage. Sometimes it contains more or less alcohol in it, but this is essentially also produced from maize. So it is some alcoholical beverage that can be used by their ceremonial activities. So Moquegua Valley, southern of Peru. So this is located between the Pacific Ocean and the Tiwanaku site. Ceramic assemblages changed entirely with the arrival of Tiwanaku colonial settlement after AD 600. That is, when they started to build the monument, and the establishment of large enclaves at previously unoccupied locations in the valley. So the people from the top made enclavements in the valley at very precise places. The chicha economy and Tiwanaku. Each community also included at least one household complex with numerous storage tinanchas and in situ feature installations of chicha brewing. The vessels set into the floor, these are big vessels, in association with large grinding stones, they are called manos, and the profusion of stone hoops. I continue. This evidence suggests that maize was stored and processed beyond the demands of the household and exported to exchange partners in the highland Tiwanaku core. Nonetheless, it is yet unclear whether this exaggerated maize production indicates a centralized state tribute system. One household, for example, had a production capacity of 513 liters, a supply estimated to have been sufficient for 171 people. So for me, it is industry. The implication that ordinary households in Andean states might produce and serve chicha in quantities so far above household needs could help to explain three of the most puzzling aspects of the Tiwanaku phenomenon. But they don't think of our system, they were thinking of their traditional way of using chicha. For us, this exaggerated production was not for beverages, but for stone making. So several people tried to discover the secret of this stone making. For example, you can read in the internet things that have been done, published in 1960s. For 14 years, that is, before 1960s, Father Lira studied the legends of the ancient Andes and finally managed to identify the Georgia shrub as the plant that, after being mixed and treated with other vegetables and substances, was able to turn the stone into mud. The ancient Indians dominated the technique of massification, says Father Lira in one of these articles. So this is the translation in English of an article written in Spanish. Softening the stone that they reduced to a soft mass that they could mold with ease. The priest performed several experiments with the Georgia shrub, and he managed to get a solid rock to soften, almost to liquefy. It does not say that it has been limestone, but it must have been limestone. However, he failed to harden it again. So he failed to harden it again. So he considered his experiment a failure. And this has been the reason why 40 years ago we also stopped. We can disaggregate, but we were not able to re-agglomerate and harden it again. I waited to get the right knowledge, and this knowledge we started to obtain only 1 or 2 years ago. Research target, we have disaggregated, we have to find the hardener, how to reconstitute. And the basic chemistry is developed in my book, chapter 13, phosphate-based geopolymers, chapter 14, organic mineral geopolymers. So, research target, finding the hardener. Where can we find there the chemicals that will generate this reaction locally? For sandstone, we found the natron for the big megaliths. For the volcanic andesite stones, we have an organic binder, acidic medium, and we are looking for the hardener. I came to the crazy idea because of all the information that I have no time to disclose here, that it should be the guano that has been extracted from Hilo on the Pacific Ocean. The guano that you find, that is commonly used as a fertilizer, and that was transported by Yama caravans to the highlands. The guano is an excellent fertilizer, but it is not the reason why they transported it to the highlands. In the Tiwanaku civilization was created before they exploited the guano. They had, at Tiwanaku, developed a very special agriculture. We did not need this type of fertilizer. They had their own fertilizer on the top. So to claim that the guano had been sent to the highlands because they needed it as a fertilizer for the agriculture is nonsense. This civilization was developed by itself. Research target, finding the hardener. This is the analysis that was carried out 150 years ago on specimens of Peruvian guano. So we find uric acid, oxalate of ammonia, muriate, this is chlorine, calcium chloride, phosphate organic matter, phosphate of lime, calcium phosphate, with some phosphate of magnesia, calcium oxalates, oxalate of lime, and water. And if we add some of the carboxylic acid that we have been manufacturing either for mice or other plants, the ammonium oxalate will be transformed into oxalic acid. Phosphoric acid will be transformed from phosphate of calcium. Calcium phosphate with acetic acid produces phosphoric acid. Ammonium oxalate with acetic acid produces oxalic acid. So we have our acids that will start the chemical reaction. Do we have some archaeological records on these caravans and trains between the guano of Ilo and the Tiwanaku, going up from the sea level to 3,800 meters? Well, there's here text on guano-llano caravans between Ilo, Moquegua, and the Altiplano. This has been published in the archaeological studies in Leiden University in the Netherlands in 2005 by Willy Minkus, and I've read. El Descanso, this is near Ilo. El Descanso means the resting place in Spanish. This name has been transmitted orally and refers to the traditional use of the site as resting place for the Llama caravans on their way to or from the highlands via Moquegua. The guano trade, appears to have been intensified during the Tiwanaku phase of construction, possibly stimulated by the need for more guano. Early colonial documents state that Llama caravans carried this trade item. The coastal Ilo population received coca, camelid wool, dried meat, as well as llamas for guano transportation in exchange. So we visited the Ilo site, the Punta Coles guano site. This is a natural reserve. We have the birds making their guano, and we took a sample of the guano. Under the optical microscope, this is how it looked like. This is a 1 millimeter scale. And under the electronic microscope and the analysis, this is what it looks like. Carbon, nitrogen, and the rest. So we have the organic matter in volcanic andesite stone. Does it contain guano? Or remains of guano, or guano that has not reacted? If we compare the EDS spectrum from the Pumapunku monument, we have the carbon, the nitrogen, sodium, magnesium, aluminum, silicon, phosphor, sulfur, chlorine, potassium, and calcium. Can you imagine chlorine there? This is the monument. This is the guano. Carbon, nitrogen, sodium, magnesium, aluminum, silicon, phosphate, sulfate, chlorine, potassium, calcium, and iron. We have the same components, but in the stone it is diluted, which seems obvious. But it is the same chemistry. Conclusion. The SEM study of a sample taken from the Pumapunku Grey Andesite monument shows the presence of organic matter. It could be the binder. We have carbon, nitrogen, and the like. This feature is very unusual in a volcanic stone. It is a unicum and supports the idea of artificial andesite geopolymer concrete. To make their geopolymer andesite concrete, the builders may have transported non-consolidated volcanic tuff, sand size, from the Cerro Capia site. They used an acid-based geopolymer technology involving carboxylic acid manufactured from local biomass, which reacted with a hardener based on guano, transported by Yama caravans from the Ilo coastal area up to Tiwanaku. The andesitic architectural elements of finely sculptured patterns are made of ancient geopolymer cast 1,300 years ago. To sum up, we have the red sandstone megaliths. This is an alkaline geopolymer, 1,400 years of age. And we have the gray andesite structures, acidic geopolymer, 1,300 years of age. Relying on the old legends with plants extract capable of softening stone. What next? The gate of the sun is andesitic, dating to the same period. Is it ancient geopolymer? What about the Cusco walls, 450 kilometers up north? Are they of the same material? Is it andesite or is it limestone? We see that they are both. Are they using the same method? We don't know. We have not studied it. But these are only questions. What next? No modern analysis for the presumed geological source at Cerro Capia volcano. There are several types of andesitic material, so there should be several types of source that we have to study. These studies should be carried out with our Peruvian geologists. The team on the site, our geologist, Luis Huaman from Arequipa, and Ralph from Geopolymer Institute. This has been my talk, Ancient Geopolymer in South American Monuments. And this is the replica that we made in the lab here of the formula using modern chemicals. It works, there's no problem. This is the white replica of a red sandstone block, and this is the white replica of an volcanic andesite block with the same chemicals but different minerals as fillers. So this is the last slide. This is something I've been personally astonished about what we discovered. I think it is it is the beginning of a very complicated, detailed research, but this is the bottom line that we have to follow. And I'm asking our South American friends to raise the question, why not in Colombia? Why not in Mexico? Why not in Peru? We know, and so forth. But then how to start studies by introducing the knowledge of geopolymeric reactions. Okay, thank you for your attention.